okay?
Yeah.
So you can't solve for all components of the metric, and to see why, I'm going to show you an example which you've seen before, but maybe not in quite the same way. That's actually analogous to what's going on in 3+1 gravity. And this example is electromagnetism. So in electromagnetism, I'm going to take the variables that I want to solve for to be the 4 potential, which I can write as phi the scalar potential and A the vector potential. The equations are Maxwell's equations, which I can write in this form. Using this F electromagnetic field strength tensor, where F, remember the definition of F is this anti-symmetric partial derivatives of A, and J, if you write out J in components, J is minus rho the three-dimensional current. So I'm going to write this out in the same sort of 3+1 form that and then after I do this, I'm going to do the same thing for gravity. So the first thing I'm going to do is make a definition, just to make the equations look easier. I'm going to define something, believe it or not, called E. And I'm going to define E to be minus d by dt of the A vector minus grad phi. That's just a definition. And using this definition, now I'm going to write out Maxwell's equations, and I'm going to write out all 4 components. So for alpha equals 0, remember this beta is contracted, so there's only 4 components here. For alpha equals 0, what I get, if I write this out, substitute in everything, and start turning the crank, what I get is divergence of E is 4 pi rho, which you should be familiar with. And if alpha is 1, 2, or 3, what I get is a component of d E dt is curl A minus 4 pi j. And if I want to sort of complete the system, let me just copy this equation over here, but I'm going to just change it around a little bit. D by dt of A is minus E minus grad phi. So that's still the definition. So now what I have this equation, which I'll call, let me call it E1. I have this equation, which I'll call E2. And I have this equation here that I'll call C1. And if you're wondering about the other Maxwell equations, they are satisfied automatically by using a vector potential. So the divergence of B is satisfied automatically just because B is the curl of A. And the d by dt of B is satisfied automatically by taking a look at partial time and space derivatives commuting on A. So these are the only ones that we really need to worry about. So why do I call these E1, E2, and C1? This C stands for constraint. And that's because this divergence of E equation constrains the value of E that you can have at any particular time. And then these two equations I call E1 and E2, E stands for evolution equations, because these tell you, given a particular value of E and A at a particular time, these equations tell you what happens to A and E as you evolve into the future. So, if you go back over here, if you want to solve the initial data problem, to solve the initial data problem, you give an A, and you have to pick an E such that this is satisfied. To solve the evolution problem, you start with the solution of the initial data problem, and you evolve these equations in time as you go up. And I want you to notice something. There is no equation for the scalar potential. This scalar potential sitting here just sort of tags along for the ride. And in fact, you can plug in anything that you want, and you still get a valid solution of Maxwell's equations. And this is the gauge symmetry associated, or one way of writing the gauge symmetry associated with electromagnetism. And the same thing is going to happen in relativity when you do the same thing. So now let me do this for relativity. And you'll find that you'll have analogous equations for relativity as you have for electromagnetism. So the first thing that I'm going to do is start out by writing down the metric. I told you that I'm not specifying the metric. Well, I'm not really. I'm just going to write it in a particular way. And where I've defined three new functions here. Let me do this one first. This gamma ij is the 3 metric. And I'll say a little bit more about what it means in a second. Let me just give all of these guys names. This is a lapse function. And this beta that appears in 2 places is called the shift vector. So the first thing that I want to point out is that I really haven't specialized. All I've done, this is like saying that the scalar potential, or sorry, that the 4 potential is made up of a scalar potential and a vector potential. And all I've done is I've said that the 3-dimensional metric is made up of these 3 different functions. So this is still general, or mostly general. So now let me tell you about what these functions I've defined are and how you interpret them. Give you some sort of meaning to go with the names. So the first thing is it's the easiest. Let's look at what the 3 metric is. 3 metric measures spatial distance. So let me draw a picture. So this is space along this axis, and this is time along this axis. And so what I'm going to do is I'm going to take this 4-dimensional space-time, and through it I'm going to draw a 3-dimensional surface. And I'm going to give this 3-dimensional surface a name. I'm going to call it t equals 0. So what this gamma ij is if you're only living on this 3-dimensional surface and you want to measure proper distances between points, you use this gamma ij as a 3-dimensional metric. So ds squared, put a little 3 there, meaning it's on the surface, is gamma ij dxi dxj. So this is just like you would use, just like you would do for a 4-dimensional metric, except it's just a 3-dimensional metric on this surface. And its signature is positive because it's spatial, so there's no funny minus sign. So now let's go to the lapse function. What does that mean? What this does, this measures proper time compared to coordinate time. So this is one function that you can choose that represents the coordinate freedom that you have in general relativity. So what do I mean by that? There's a particular rule that you use. Suppose I'm at this point here, and suppose I have another surface that I call t equals delta t. Then if I want to be able to get from here to here, I draw a normal vector, and I follow that normal vector by a distance alpha delta t, where alpha delta t is now the proper time that it takes to go from here to there. So as I said there, this alpha just tells you when you go a coordinate time delta t from here to there, how much proper time has elapsed. So this is d tau at this point. And so sometimes what you like to imagine is you like to imagine a set of what are called normal observers in order to pick your coordinates. And here's what I mean by normal observers. Imagine that you have a graduate student that you put out in space-time, and you give that person a name, and you say, your x equals 5. Then you have another graduate student that you put here and say, your x equals 4, and so on. Then you can think of these normal vectors as the world lines that these graduate students travel along. So what alpha measures is it measures the proper time of one of these graduate students, one of these normal observers, as they travel from t equals 0 to what you call t equals delta t. And let me just note that if alpha is constant in space, if alpha is constant in space, then normal observers move on the UD6. But if you wanted to, you can give each one of these graduate students a rocket engine and let them accelerate, and you'd have an alpha that's not constant in space. But this is just a way of parameterizing your coordinate freedom. So now, what's this shift vector? This is the last piece in here. The shift vector measures velocity of, this is going to sound funny, but let me explain what I mean. It measures the velocity of spatial coordinate labels. So here's what I mean by that. Suppose I call this point x equals 5, right here. And this point corresponds to one of these normal observers. Then this normal observer follows his world line and eventually gets up to t equal delta t. Well, I don't have to still call this point x equals 5 anymore. If I wanted to, I can call this point over here x equals 5. That is, I can have the spatial coordinates be moving with respect to the normal observers. And the way that you parameterize that is, if this is your normal vector here, this is your shift vector, this is alpha t, then this shift vector just is an extra vector that's added so that you get, it gives you a vector that will go from x equals 5 here to x equals 5 here. So just think of it as the velocity of your coordinates. And it's often useful to have such a thing, to make your coordinates move with respect to normal observers. And I'll just give you a quick example. I'll just tell you, for a black hole, normal observers, if they actually are graduate students with rocket engines, unless they're really accelerating well, they're going to tend to fall into the black hole. And if you're doing a simulation, you don't want all your coordinates to fall in. So you can use this coordinate velocity to keep them out of the hole. So that's what those variables are. And I unfortunately covered up the picture. I'll move that down right there. So in order to make Einstein's equations look nicer, there's one more variable that I want to define. Remember, for E and M, I define this E field for E and M. For GR, I'm going to define something that has a name that sounds very good. Something that's called the extrinsic curvature. The name sounds a lot worse than the thing actually is. Kij. And this is going to be this is going to be defined very much like E is defined. It's going to have the d by dt of the metric in it, of the 3 metric, just like E had d by dt of the vector potential. And then it's going to have other terms. So it's going to have shift terms, basically. And another term. And this is really the same idea as what I did here by defining the E. So it's d by dt of the vector potential and then minus a grad of the scalar potential. Here, k is d by dt of the 3 metric, which is sort of like the vector potential, and it's minus things that have to do with beta, which is sort of like the scalar potential. So alpha and beta are again, the gauge freedom pieces in this picture. Okay, so now I've defined this thing. And you should just think, this has a geometrical interpretation, but you should just think of this as something that gives you the time derivative of the 3 metric. So now, I can write down Einstein's equations in terms of these variables. I'm not going to write everything out, I'm just going to write a little bit. So for alpha equals 0, beta equals 0, I get an equation that looks like this. I get the 3-dimensional scalar curvature. I get things that have this extrinsic curvature squared in it. 2 terms like that. And I get a matter piece. So this is a lot like the divergence of E equation. This is called, all these equations have names. So if you read a paper and you see somebody say Hamiltonian constraint, that's this equation.
Can you explain the 3R a little bit more?
Okay, so what this 3R is you know what the Ricci scalar is for a 4-dimensional metric. This is the Ricci scalar where you use the 3-dimensional metric to compute it. So you do it in the exact same way, right? Where you can you can define a 3-dimensional gamma Christoffel symbol or connection coefficients from this 3-dimensional metric. And then you can define a Riemann tensor, a 3-dimensional Riemann tensor, in terms of derivatives of this and terms that have 2 of these multiplied and contracted. And then you can define a 3-dimensional Ricci scalar by contracting the 3-dimensional or 3-dimensional scalar curvature by contracting the 3-dimensional Riemann tensor. So this is exactly the same thing and exactly the same formulas as you use to get the 4-dimensional thing, but you just use the 3-dimensional thing to compute it. So that's what that is. So now, let's look at Einstein's equations for alpha equals 0 and beta equals 1, 2, or 3. Then what you get is an equation that looks like this. This is called the momentum constraint. Where this K here is the trace of the extrinsic curvature. Same K as in the other equation. And this slash here means take the covariant derivative of this, but it's not the 4-dimensional covariant derivative, it's the 3-dimensional covariant derivative computed with that 3-dimensional metric. And if you want to compute the 3-dimensional covariant derivative of something, you do it exactly the same way as you do the 4-dimensional covariant derivative. You correct indices using gamma terms, where the gammas that you get are gammas that are derived from the 3-dimensional metric. And this is called the momentum constraint.
And the Ji on the right.
And the Ji is the matter current. So it's a piece of it's a particular piece of this T alpha beta that's projected into the time and space direction. So it's basically the current of mass. Just like this rho is the mass density. So it's just a piece of the stress energy tensor. So these are the constraints, and these are like this divergence of E is 4 pi rho. They tell you at a particular time, what does the gravitational field have to satisfy? So these are what you would solve if you wanted to look at the initial data problem. So now, let me put down what happens if alpha and beta in Einstein's equations are both spatial. And I'm not going to write out the whole equation. I'm just going to write out sort of what it looks like. So you get v by dt of kij is going to equal, it's going to have something that has function of. So it's some function of, it's going to have a 3-dimensional Riemann tensor in it, or sorry, Ricci tensor in it. It's going to have k's in it, it's going to have betas in it, and it's going to have alphas in it.
Which of those is it linear in? Which of those is it linear in?
It's linear in betas and alphas, but and in well, alpha is linear with itself, and beta is linear, but there's alpha multiplied by all kinds of other things. It's nonlinear in K, and this Ricci tensor is nonlinear to begin with. So it has terms. So it has terms that look like this, and then there's K squared terms with an alpha in front, and then there's beta terms that are only multiplied by derivatives of K and derivatives of beta. So there's beta dk and K d beta terms. So there's nonlinearities in a few places. One is where you have the K squared terms. The other, if you want to call these nonlinearities because they're between different variables, it's still nonlinear. But this term is linear in beta, and you have nasty nonlinearities in this Ricci tensor. And let me also tell you that this K squared is more nonlinear than you think it is when you just look at it as K squared. because this k-squared also has inverse metrics in it as well. Right, so it's quite nonlinear.
So there are no time derivatives on the right-hand side.
No, there's no time derivatives on the right-hand side at all. The only time derivative is here. Yes, thanks. That's an important point. And this equation, where it says time derivative of k equals something, this thing is like, it's like the time derivative of a equals, sorry, like the time derivative of e is the curl of a plus the matter term. There's also matter terms here too. And just like in electromagnetism, where you have no equations for the scalar potential, here it turns out that you have no equations for the lapse and the shift, which are, again, these are the functions that tell you about the coordinate freedom or the gauge freedom that you have. So, to solve the initial data problem, you would solve these two constraints, which have nothing to do with the lapse and the shift, except implicitly through the definitions of k. And to solve the evolution problem, given a solution of the constraint equations, you would solve this equation and this equation for d by dt of gamma ij, just like you did over here in E and M. So they're quite similar. Of course, there's some important differences. And I think one important difference is that in this case, as you know, in E and M, if you define B as curl of A, you can write the equations in such a way that all the gauge freedom is gone and everything's gauge invariant. Here, you can try to do something like that, but it's not going to work. Because no matter what you do, you're still going to have metrics in everything. So you're not going to be able to eliminate the gauge freedom like you did here where you can eliminate the vector potential. So let me say quickly, how do you choose as I said, there's no equations for alpha and beta. You can choose them to be whatever you want. Well, how do you choose them? I can tell you two things about how you choose them. Number one is the strategy is sort of the same as for E and M. You want to choose them to make the solutions look nice, and you want to choose them so that nothing, so that they give you your equations particular properties that you want. The second thing that I want to tell you about how to choose them is that nobody really knows how to do it well. And this is an unsolved problem and a topic of intense current research in numerical relativity is exactly how do you choose these lapse and shift functions in such a way that your coordinates are nice. And by nice, I usually mean that very nasty things don't happen like singularities. So let me close by just talking about very quickly a few sort of the current status of our ability to solve these equations, sort of what can be done now, what are we trying to do in the future. So what can... And all of these things probably deserve an entire lecture or maybe a course, but I'm only going to be able to mention them. So one thing that has been done is black hole formation in various models. So black hole formation by star collapse, or black hole formation by gravitational waves imploding on themselves and making a black hole, which can happen because gravitational waves carry energy. So if you have enough energy concentrating at one spot, you can form a black hole. Other things that can be done, single black holes with radiation. So you can have single black holes that are distorted, not a stationary Kerr or Schwarzschild state, such that they ring down and produce radiation. You can do things like that. Another thing that's been done is Quasi Equilibrium neutron star binaries, black hole binaries, and one that I know of, black hole neutron star. By Quasi Equilibrium, I mean you solve the initial data problem in such a case that what you hope to get is a snapshot of a binary orbit. And in order to do that, you actually have to make, you can solve Einstein's equations exactly for the initial data problem. But what you don't get is you don't necessarily get the correct gravitational wave content of the solution. So you have to make various approximations to try to figure out what that gravitational wave content is. So if you really want to do the whole problem, you have to take into account radiation. And this really is a steady state solution here. So these sorts of things have been done. Black hole collisions have been done, both head-on collisions and grazing collisions. And by grazing, what I mean is something like this, where the two black holes are separated a little bit, given an impact parameter, and you could watch them in spiral, or you can watch them merge. No, in spiral. Same with neutron-neutron star mergers. In fact, there was just a paper that came out on the web, I think it was today, by Shibata, that where they do a very nice simulation of neutron-star merger, and you can see black holes forming in some cases, or you can see the normal modes of the neutron star ringing down in other cases, and so they can get both black hole and neutron star final states from this. What can't we do yet?
I'm going to cut you off in 1 minute.
Okay, 1 minute.
Another class coming in.
What we can't do yet is black hole evolutions in spiral plus merger. So what we would really like to do, and this is a topic of intense research right now, is to have your two black holes, to actually stick them at some distance apart, solve an initial data problem for them, and then be able to evolve them long enough that they make several orbits and merge and collect the gravitational waves from them. And we'd love to do this, and it's something that we're working on among various other things that I don't have time to talk about. But let me close by saying that numerical relativity is opening up new possibilities in what we know about the Einstein equations, where we actually have the possibility to solve some of these problems that you could not have even dreamed about solving maybe 10 years ago.